Chapter 6 is trigonometric functions, and we're going to start with some review from grade 11. This symbol you see here can be read as a square root of 4 or radical 4. That's because that symbol isn't just a square root sign, it's also called a radical sign. What's under the radical sign is called a radicand. And we'll do some examples here. Square root of 45. The question says simplify. So what that means is you need to think of numbers that are factors of 45, which are also perfect square numbers. So the perfect square numbers, you know, we're not going to count 1, but the next one will be 4, 9, 16, 25. Those are all perfect square numbers. You need to find one. Think of one that is a factor of 45. 9 times 5 is 45. So instead of writing 45, I'm writing it as 9 times 5. And I can break that apart from the properties of radicals you learned in grade 11. You can break it into two completely separate radicals like this, 9 times 5. Now the square root of 9, we can simplify. The square root of 9 is 3. So the answer is 3 root 5. This is called a mixed radical, and this is an entire radical. So just like with fractions, you always reduce to lowest terms. So when you have a square root number like this, you have to reduce it if you can to a mixed radical if possible. So what happens when we have kind of like a coefficient, a leading coefficient in front of it, or part of the radical that you have both pieces? You have a whole number or an integer as well as the radical. So again, what are factors of 32? Can you think of a factor of 32, which is also a perfect square number that we would be able to square root? So maybe you're thinking 4. 4 times 8 is 32. That's true, but there's a bigger one. 16 times 2. So breaking apart the 16 and the 2, the 16 turns into a 4, and then the square root of 2, we can't do that. Students sometimes want to say that square root of 2 is 1, but it's not. Just think about it for a second. It's not. So we have two integers now. We have negative 3 times 4. We multiply those together and we have negative 12 root 2. But if you were thinking, as I said at the beginning, well, you were going to write instead, you were going to put negative 3, and instead of the square root of 16 times 2, you were thinking of 4 times 8. Okay, that's a negative 3, and the square root of 4 is 2, and then you have root 8. So we put 3 times 2 together, we get negative 6 root 8. But notice that that square root of 8 is not in lowest terms yet. You can still simplify that radical. So you would pull out, you would do this all again, just like if you're reducing a fraction and you didn't reduce it enough, you'd have to keep going. So we would have to keep going here and write that as negative 6 times 4 times 2. And then you would pull that out and you would get the same answer that we got here once you finish the question. Part C, square root of 5 times the square root of 7. Okay, the instructions said simplify. I can't break those down. Those are prime numbers, so I can't break them down. The only thing I can do is what the question is saying, which is to multiply them. So I get the square root of 35. Sometimes when you multiply two radicals together, you get a new one that can be reduced, but this one can't be. So this is as much as I can do with this question. D, square root of 48 over the square root of 6. So there's a couple of different ways we could do this, but I just want to show you that you can write this as 1. You can divide them together as a square root of 48 over the square root of 6, which is the square root of 8. So I could have reduced this first, but I just decided just to do straight division. 48 divided by 6 is root 8. Now you have to look at your answer here, the radicand. Can that be reduced at all? It can. The square root of 8 we can write as 4 times 2, and that becomes 2 root 2. We have one more, root 2 over 9. So as opposed to this one where I had the radicals separately, a numerator denominator, here I put it all together. But let's just break it up again. And you'll see that the square root of 2 stays the square root of 2, but the square root of 9 we could reduce to a 3. So that's how we can do division as two separate pieces, like this numerator denominator, or we can write it all as 1. But the point is to choose the one that will allow you to reduce the fastest. And What should your answer look like if the question says simplify like this one did? Simplify means your final answer needs to be a radical in lowest terms, means needs to be reduced. If you have a radical left like this root 2, you cannot reduce it further. You can't break it down anymore. So if you had done this step here and you stopped at -6 root 8, you would not have been fully simple. You've not fully simplified yet because you could still break it down further. We have one more slide with radicals and we'll move on to trigonometry. Example 2, collect like radicals. So simplify, sorry, the instruction says simplify, and you've got a little strategy here that I put. Simplify here. So I have to follow the order of operations. The power of 2 means write it out twice. It does not mean work in reverse and square this piece and square this piece. That's not what it means, because so you can't do that. And that's because of this minus sign in the middle here. Because of that minus sign, I can't distribute. If I had 3a squared b to the power of 2, then I can just, because that's one term right there, then I could distribute the 2 backwards, get 9a to the power of 4b squared. That would be okay. But because of this minus sign in here, we can't do that. So let me erase all that. All right, so we write it out twice, and now we have to distribute. This is binomial distribution or expansion. So the first term is multiplied by the first term. So we take integer times integer. That's going to give me a 9. And then we multiply radical by radical. So root 3 times root 3 is root 9. Next one, we take 3 root 3 times -5 root 2. So integer times integer. That's the 3 times the 5. That gives me -15. And then the radical times the radical. So that's a root 3 times root 2 is root 6. Next one are the inside terms. Integer times integer will give me -15. Radical times radical is root 6. And the last one is the very last terms. 2 negatives are going to give me a positive 25. And root 2 times root 2 is root 4. Okay, what can we do with that? So 9 root 9, of course, is 9 times 3. That was nice and easy, broke down nicely. 15 root 6, so is root 6, can that be broken down at all, like we did in the previous examples? No, but what we have got are like terms here. So we've got 15 root 6s, sorry, -15 root 6s, subtract another 15 root 6s. If you want, you can think of those root 6s as an x. If you want, they're like terms. There's an x, there's an x. So we have -30 root 6s there. And then we have plus 25 square root of 4 is 2. So that gives us 27 minus 30 root 6 plus 50. And our constants can be collected to 77 minus 30 root 6. You can write it either way. You can put the -30 root 6 first and the 77 after. Doesn't matter. For correct form in mathematics, we never have a radical in the denominator. To rationalize the denominator, we need to multiply the denominator by its conjugate. What is that all about? Okay, example 3. Rationalize the following denominators to simplify. So the first one here, rationalize the denominator. This is an irrational number. The square root of 2 is irrational. That's what it's part of the real number system, right? It's a real number, just like integers are, whole numbers. These are irrational. So we're not allowed to, in math, have a irrational number in the denominator. So we need to get rid of that. Well, this great strategy that we have in math, it's so simple, it's hard to believe that, you know, it's not used more often, but we're going to multiply this whole thing by 1. So we're going to multiply by 1. Why would we do that, right? Well, we're going to make the 1 look pretty helpful to us. So my 1 is going to be a root 2 over 2. This is just 1. But by multiplying by 1, this is a great strategy. By multiplying by 1, you can see what's going to happen with my denominator now. It's going to be rationalized. So what I'm going to have in my denominator now is, let me write the denominator first. Root 2 times root 2 is the square root of 4. It's just 2, but I'm just going to not skip that step. Then I multiply the numerators together and I get 3 root 2. So that simplifies to 3 root 2 over 2. Now I have a rational denominator. If it happened that this weren't a 3 up here, let me just change it to an 8 for a second. If I had an 8 there, then I would cancel these two out, and I would keep going because they're both integers. But let me just put it back to the way it was. Our correct answer is 3 root 2 over 2. Now the root 2 and 2 are not the same. You're not going to cancel those out. And if you don't believe me, you can go to your calculator and you can type in root square root of 2. The square root of 2 is not 2, so don't cancel these two out. Next one. This one's a little harder. I can't have that root 7 in the denominator. That's irrational. I'm not allowed to have that. But this is a binomial here. I can't just multiply by root 7 over root 7 like I did for example A. Because if I multiply by root 7 over root 7, let me write that down. If I tried that, times root 7 over root 7, once I distribute here, I'm going to end up with a 4 root 7 plus, these will be gone, but I'll still have a radical there. So I can't multiply by root 7 over root 7, and this is something we did last year, so maybe you remember what we did. We're going to multiply by the conjugate. And that's what it says in your box at the bottom here. We multiply the denominator by the conjugate. So you've conjugated in French class, right? So we're conjugating here. We're taking this, whatever the sign was in the middle originally of your binomial, you put the opposite sign here. So in your homework, if you have a question that's a minus here, then you put a plus here. But here's my 1. This is my more complicated one, but this is still 1. So I'm not changing my question at all. You multiply by 1, you're not changing anything. So that's why I'm allowed to do that. It's a little more complicated to multiply it out, but let's do each step here. We've got, so 1 times 4 is 4. 1 times negative root 7 is negative root 7 over, now I have binomials here. So I'm going to have to do this question like example 2. So first I'm going to do 4 times 4, that's 16. Then I do 4 times negative root 7, that's negative 4 root 7. Now the inside, now maybe you can see what's happening here. This is plus 4 root 7. And see what's happened here with these two terms? And then I multiply my last piece is negative root 7 times positive root 7 is negative root 49. Let's move this across. So 4 minus root 7, the numerator, I can't do anything with that. But the denominator, so these two cancel out, and that's supposed to happen. That's why you had one negative and one positive, so they're gone. This one reduces, and we end up with 16 minus 7, which is 9. So that's how we rationalize the denominator when we have a binomial in the denominator. So that's the end of our radical portion. Now we're going to move on to some trigonometry. Trigonometry review. Okay, this is all these bullets you see on the left-hand side. I'm going to be using them probably all of them throughout the examples we're going to do. They're going to come up at different times, but these are all words that you should know already from grade 11. I'm going to start with just this little thing right here. Sine of theta equals a number. In this case, theta would be our input, because you'll hear teachers using the words input and output a lot with functions. You have one input, you get one output. That's the output. So you put in some number for theta, sine of 60 degrees, you get an answer, you get the output. Over on the right is just some review of grade 11. this box here, this is to remind you of when you're on, this is a unit circle. A unit circle has a radius of 1, like this, see this one right here? It has a radius of 1. That makes it a unit circle. When you are using the unit circle, cos is the same as you know from grade 10, adjacent over hypotenuse. Now the hypotenuse on this circle is always a 1. And the adjacent side will be the x. Here's our theta in the middle. So the adjacent side is the x. So we're going to get x over 1 for adjacent over hypotenuse, x. So when you're on the unit circle, cos is the same as your x value. Sine is the same as your y value because the hypotenuse is always a 1. The question we're going to do is draw cos of 120 degrees in standard position. Use special triangles to determine the exact trig ratio. So the question says draw, so we have to draw. We have to use a ruler. Now the ruler with this tablet and this pen that I'm using really don't work very well, but you guys should be using a ruler. Mine might end up coming out pretty rough here, but we're going to start by just drawing an x and y axis. Okay, 120 degrees. I'm trying to draw 120 degrees. What quadrant is that in? Remember your quadrants. Use capital Roman numerals. This is 1, 2, 3, and 4. 120 degrees. Let me add some more information on here for you. If I'm going to draw a line right along the positive x-axis here, this light blue line I'm putting in, this is called the initial arm. So this is where I'm going to start drawing from, initial arm. It's the first thing on your bullet list there. So I'm going to rotate from my initial arm counterclockwise, the same direction that the quadrants are labeled. I'm going to rotate around 120 degrees. So where's 120 degrees going to land? Well, let's just label, if we're at the top of the y-axis, that would be 90 degrees. All the way down to the other side of the x-axis is 180 degrees. At the bottom of the y-axis would be 270 degrees. And if we rotated from the initial arm all the way around, we would be at 360 degrees. If we didn't rotate at all, we would be at 0. So this is being right on the x-axis is either 0 or 360 degrees. We're going to rotate 120 degrees. So you would be measuring this, if you could, with your protractor. Okay, so I didn't measure that because I don't have the tool for this to do that. This rotation right here, starting at the initial arm and going all the way, rotating around to here, that should be 120 degrees. So the spot where I landed is called the terminal arm. That's the second bullet in your list there. The terminal arm is the new blue line that I drew. That's called the terminal arm. That's 120 degrees. So that is a, let's look at our list here. So we went over initial arm. Terminal arm is there. Positive rotation is what I just drew. When you draw counterclockwise, it's positive rotation. Negative rotation is going the other way, is going this way. That's a negative rotation. Principal angle, that's what the question asked me for. 120 degrees is my principal angle. Related acute angle. So let's see what that is. Related acute angle, that means when you draw a horizontal line to the x-axis from your terminal arm. So I'm going to draw kind of a green dotted line coming down here. It's supposed to be straight, 90 degrees. That new triangle that I've just drawn in quadrant 2, it has an angle measurement of 180 minus 20. It has an angle measurement of 60 degrees. That is my related acute. And we often use the Greek letter beta for related acute. So my related acute here is 60 degrees. My principal angle was 120. Okay, standard position just means I used a counterclockwise rotation, so I'm in standard position. Co-terminal angles, we'll talk about that one in a minute. Okay, so the question again said, draw cos of 120 in standard position. This is standard position because I started at the positive x-axis. I rotated from the positive x-axis. I rotated counterclockwise, and I drew a new arm. That's standard position. Use the special angles to determine the exact trig ratio. So now I want to figure out exact cos 120 degrees exactly. I'm not going to get out my calculator and we will often have a non-calculator quiz or test in this unit, so don't be pulling out your calculator all the time. So I'm looking to find cos of 120 degrees exactly. Remember that cos is adjacent over hypotenuse, but on this unit circle, actually I'm going to write these all up here for you. Sine of theta is always y over r. Cos of theta, r is the radius, which is also the hypotenuse, x over r. And tan of theta is y over x. So then we reverse them for cosecant, secant, and cotangent. We reciprocate them. So back to our question here. Cos of 120 is adjacent over hypotenuse. On this unit circle that I'm drawing here, on this diagram, I'm putting cos of 120 is the same as the x over r. Okay, you can, either of those are fine. So looking back to my little triangle I drew over here, I'm going to use my related acute angle because I have a triangle that I learned in grade 11 and memorized that has an angle of 60 degrees. Put that over here. The special triangles, and normally I would draw them with a ruler, but I'm just going to freehand draw them here. So this one, when I have I have a isosceles triangle here, two side lengths are 1, the legs are 1, the hypotenuse is √2. That will be the 45-degree triangle. Both angles are 45 degrees. The other triangle you have memorized from last year is the 30-60 triangle. So this corner is 90, the hypotenuse. The small one is the 30, the big one is the 60. And across from the 60, the side across from the 60 is a √3, the hypotenuse is a 2, and the smallest side is a 1. So I look at those triangles, and from them, so I'm looking for cos, I'm going to find cos of 60. I'm going to find the cos of the related acute. So cos of 60, I go to my 60, cos is adjacent, that's 1, over hypotenuse, that's 2. So cos of 60, cos of 60 degrees is 1 over 2. That's related to cos of 120. The only difference is the signs. We might have a positive or a negative. We have to figure out if it should be positive or negative. So cos of 60 is definitely 1 over 2. Is cos of 120 also positive? So let's go back to the cast rule. Cast rule, the C starts in quadrant 4 in the bottom. That's cos is positive there. All sine, cos, tan are all positive here. Only sine is positive in quadrant 2, and only tan is positive in quadrant 3. So our question, 120 degrees is in quadrant 2. In quadrant 2, sine is positive, so cos is negative. And since we're doing cos, that means our answer is cos of 120 degrees is going to be negative 1 over 2. So it's going to be the same answer as cos of 60. It's related, right? It's related to it, but you just have to think about whether or not it's positive or negative. You have to look at the cast rule to figure that out. So cos of 120 degrees is negative 1 over 2. Part B says determine the values of theta. Tan theta equals 0, and there's always a restricted domain in these questions because we can have infinite answers. So we're only looking for the answer between 0 and 360 degrees. Tan theta equals 0. So we don't want to focus on our calculators here. It doesn't ask me for a sketch, so I don't have to be accurate here, but I am going to do a sketch because I find them very helpful. So draw a quick x and y axis here. This is x, this is y. Tan theta equals 0. So remember looking up here to the sine, cos, and tan that I wrote earlier. Tan is y over x. tan is y over x. Let me write that down here. Tan theta is y over x. Now we know it has to equal 0. So tan theta equals y over x. So is the y 0 or is the x 0? It's got to be the y, right? Because x, we can't have a 0 denominator. If I had some number over 0, well, that would be undefined. It wouldn't be 0. So I have to have 0 in the numerator. That means my y value has to be equal to 0. So therefore, y equals 0. And x, well, we'll see what x is going to be. So my y is 0. Where on this Cartesian plane here, where on this little grid is y equal to 0? Or look at this one up here. Where would I have a y value of 0? So y is 0 when we are at, imagine a circle right here. Let's pretend that's a circle. So we've got 0 and 360 here. This is 90, 180, 270. Where is y equal to 0? Y is equal to 0 right here on the unit circle and right here. On the x-axis, we have no y value. So the coordinate of the first one is 1, 0. The second red dot I made, its coordinate is -1, 0. So that means when I'm going to draw in my rotation, here's my initial arm here. I am not going to rotate it all first, so 0 degrees is one answer. But I could also rotate over to here. So if I rotated 180 degrees, tan is also going to be 0. And because my restricted domain says I have to go all the way back to 360, I'm going to go back here again, and 360 degrees is an answer. That means tan of 0 is 0, tan of 180 is 0, and tan of 360 is 0. Well, in this case, we were given the output. We were given the number, the answer at the number. We were told that the answer has to be 0. What's the input going to be? And we have 3 different answers, and of course that's possible. You can have many different answers here, but you have only one output. So the previous question I did, if I asked you when is cos, if I didn't give you the 120, I would say when is cos equal to -1/2? Well, then you would do the whole question in reverse. You would try to find a triangle that has a ratio of an adjacent over hypotenuse of 1/2 to work backwards to get this answer. So we're just using these values here, subbing in. If you're given the answer, you're given the output, you're subbing them in here, and then you're working backwards either with the unit circle like this one or with the special triangles to find a match, to figure out how could I get that 1/2 or how could I get that 0, working backwards to find the input. Part C, determine the angles for each equation and draw a diagram to represent it. Okay, here is a unit circle because the radius is 1. The circle reaches 1 on the x and y axes. So the first thing I'm going to do is remember that on the unit circle, the radius is 1. So since cos is x over r, or adjacent over hypotenuse, since cos is x over r, my x must be 0.51. So I can ignore this r is 1. X has to be 0.51. So I go along my x-axis to 0.51. So once I'm along the x-axis at 0.51, now I need a triangle. So I'm going to go up to the unit circle, and I'm going to draw a line up from 0.51 to touch the circle, put a dot there. So that's going to be my angle. I want to measure from the origin to the dot. Positive rotation means in this direction, so you're reading carefully to see what that rotation looks like. Draw a line through there, and on the one I have here, it looks like I would say, whoops, it looked like it was about maybe 58 degrees, something like that. So without a calculator, because you will be tested without a calculator, you have to be able to do it like this. Cos of theta equals 0.51. So there's no getting out your calculator and doing inverse cos. You have to know what this means. So this is an estimate using a drawing and just the best guess you can. Theta is going to equal whatever you get. It should be around this number. I think the actual answer is 59 degrees. So however close you can get on with your sketch. That's how you find the angle without a calculator and without a special triangle, right? We don't have a special triangle that measures 0.51, so we draw it and try to find it without it. B, sine theta equals negative 0.8. So we're going to do the same thing. Got a unit circle. This time we have sine, and remember, sine is y. So my y value is negative 0.8. So instead of going across my x-axis, I'm going to go down my y-axis to negative 0.8. This is a y value. So there's negative 0.8 straight down the y-axis. I'm going to go over to the circle, put a dot on the circle, and then draw a line through there. And I'm going to measure, this is the positive x-axis, I'm going to measure from the initial arm all the way around. Let me draw that on there. So I'm going to, this is my initial arm along the positive x-axis. I'm measuring this right here and just coming up with the best guess that I can. So probably your protractor doesn't measure a full 360 degrees. A lot of them don't. A lot of them are only semicircles. So this whole first piece here, of course, is 180, right? You know that's 180, and then you only have to measure the extra bit. And I think I got it to be about, so theta 1, I'm calling this, let me call this theta 1. I'll explain that in a second. Theta 1 looks like it's about 233 degrees. But there's another answer. That's why it's theta 1. There's another answer because where sine is negative. So there was another answer on the last diagram too. I just doing it in steps here. The last question we did also had another answer. It was about 300 degrees, but I'm just showing you one step at a time. So we have another answer. We always have two answers. Theta 2. So we draw another line here. We do the same thing. You can finish this on your own. You're going to draw a terminal arm here. You're going to measure. So you're going to put your terminal arm in here, but you're going to use a ruler. I'm not using a ruler right now. Terminal arm there. Then you're going to measure here. That will be theta 2. And theta 2 is going to give you about 307 degrees. So the previous question also had two answers. I just started with the first one, but there's always two answers in a question like this, where you're given the output. You're given the output and you have to work backwards to find the input. There's always two quadrants because sine is negative in two quadrants. Sine is negative here and here. So we're going to have two possible places it could be. Previous one, cos was positive. Cos is positive in this quadrant, cos is positive, of course, in the first quadrant, and cos is positive down here. So you would have drawn another one down here. D, point -2, -7 lies on the terminal arm of an angle in standard position. So you should remember all of this means. Terminal arm means the angle where your angle stops, where it terminates. Angle in standard position means it's rotating counterclockwise from the x-axis. Determine primary and reciprocal ratios and the measure of the principal angle. That's a lot of stuff. Let's look at our first piece of information, -2, -7. We don't need to do a sketch. Question doesn't ask for one, but it's always so helpful. So there's my x-axis, there's my y-axis, -2, -7. So over 2, down 7, my point would be about here, -2, -7. That's where it would fall. So I'm going to draw a line to that point there, and I'm going to draw a triangle. Now your triangle is always drawn to the x-axis. You do not draw a triangle ever to the y-axis. So up to the x-axis, we have our last piece of our triangle. And now we have to determine the primary and reciprocal ratios. We need to find first theta. So here's our positive x-axis, rotating all the way to here. That is our theta. That will be theta right there. That's the principal angle. So what do I know about this triangle? Well, I know that the x value right here, right, this distance from here to here that was -2. So I know that that value there is a -2. Down to the bottom, that was a -7. So this length, I'm going to write it as a positive value there, is 7. The length is 7, but the value is a -7 here. Okay. So I've got some lengths for the size of the triangle. Now, what about the radius or the hypotenuse? I need that because I need to find all the trig ratios. So I need to find R. Find R. So that's Pythagorean theorem. We've got -2 squared plus -7 squared will equal R squared. Let me put the right angle in the triangle here. That's 4. And 49 gives me R squared. So 53 is R, or the square root of 53. So if this was a non-calculator question, I would have to reduce that radical if I can. But this question, you have some like in your homework, it will give you decimal answers. So we're going to go ahead and get out your calculators for this one. And we'll get about 7.3 is approximately the value of R. Some questions will have decimals in them, some will have the radical 53. So it just depends what the back of the book wants for these questions. Exact is square root of 53. That is exactly correct. This one we rounded, so 7.3 is approximate. Just depends on what the question's asking for. Okay, so we've got R. R is, let me put it in my diagram, R is equal to a square root of 53 or 7.3. Now what? Now the question said determine the primary and secondary trig ratios. So let me change colors here. Blue. Primary are sine, cosine, tan. So sine theta. Sine is opposite over hypotenuse, but it's a little bit easier when you're using the Cartesian plane like we are to think of sine as y over r. So our y value, so let me put that, I'm going to write on the coordinate, I'm going to just put that down here, -2, -7. This is my x, this is my y, and here's my r. So y over r is -7 over, again, depending on what the book wants, do they want the radical or do they want the decimal? If you want if they want the radical, they will probably want you to rationalize. So I'm just going to write it as -7 over 7.3. Now you would never mix decimals and fractions like this. I think your calculator does that though. I mean your textbook. Cos of theta is x over r. My x value is a -2. My r is a root 53. So if we're working with radicals, I'm going to rationalize this because I can't leave the radical in the denominator. And I get -2 root 53 over 53. And I can't reduce that further because the 2 and the 53, the integer pieces, they don't reduce. These two parts don't cancel into each other. So we've got sine, cos, tan. Tan is y over x. So that's -7 over -2, or 7 over 2. Two negatives make a positive. The reciprocal ratios are cosecant. I'm just going to squeeze them on the side here. Cosecant theta, secant theta, and cotangent theta. And all you need to do for these are flip these numbers here. They're just reciprocating them. Again, it just depends on whatever the textbook gave you. Now in this case, when I flip these two, I'm going to get a radical in the denominator again, so I would go up here and flip these two. So that's what you'll fill in for the reciprocal ratio. The last piece we have to do that the question asked for is the measure of the principal angle. So the measure of the principal angle means find theta. And we have all of these different values that we've already worked on. So you could take any of these in your calculator. So let's say you did inverse sine of either one of these two. Put that in your calculator, either of these two. Inverse sine of -7 over 53, or inverse cos. This is probably the easiest one here. Is we had tan theta equals 7 over 2. So I would just take inverse tan. So theta is going to equal tan inverse of 7 over 2. And you don't need to do all this work in the question if it didn't ask for it. I would go right to the coordinate. If all they asked for was find theta, I would just go right with tan right from the beginning. I wouldn't do anything else. And you will get your calculator gives you theta equals 74 degrees. But take a look at our graph. There's no way that red rotation is 74 degrees. Your calculator is always going to give you the smallest possible answer that it can. So your calculator if you put this into your calculator, this part here, you're putting positive values in, your calculator knows that tan is positive in this quadrant, so it's giving you the 74. So what it's actually giving you is the beta. So it's not giving you the theta, it's giving you beta. It's giving you the related acute angle. That's 74. We want alpha. So, we want theta. So theta, because we're in quadrant 3, we've got to take 180 and add on that beta angle. So let me put it up. I'm going to put it up in the triangle too. Way up here in the corner, this little piece right here, that's 74. So I need to add that on. So my final answer is going to be the principal angle, which is the one that I'm really looking for. Therefore, theta equals 254 degrees. Okay, one more. Sketch one cycle of this sinusoidal function. This is the last one we're going to do. First of all, we have to factor because our k value, that's the 1/2, isn't isolated from x. So we're going to factor that. And you can always check that really quickly. You're factoring. Multiply the 1 back into the x, you get 1/2 x. Multiply the 1 back into 60, you get 30. So you can always, it's worth it to just give that a check. So now that it's factored, you need to think of, there's so many different ways to graph sinusoidal functions. So you think of your preferred method, you've already learned it in grade 11. This is not something new. You already know how to graph. So the method I show you right now, you might say, I didn't learn it that way. I don't understand that way. You don't have to do it this way. You already know how to graph. So the method I'm going to review is one of them that helps us see the transformations a little better. They all have their benefits. This one, I'll explain it as we go. It's kind of called the coordinate equation. So this is going to be a coordinate. This is going to be one term here, a comma, and then the y value here. So x comma y. So it's going to be a coordinate. We're going to come up with new coordinates this way, and we're going to create little mini equations inside of it. So how do we do that? This isn't a table of values. I just set it up like a table, but I use these dotted lines. It's not a table of values. So first, just look at this part here. Our parent function is cos. So I'm going to just list 5 parent coordinates here, and you can get them from your calculator, but you should know some of them. So first of all, 0 and what? So think of the cos, think of the x values on those unit circles we've been talking about. 0 and, or Let's switch my pen here. You can put it in your calculator if you want to, but these should be old hat for you. 0, cos of 0 is 1. Cos of 90 is 0. Cos of 180 is -1. Cos of 270 is 0. And then 360, we're back where we started out, 1. So those are our parent coordinates. That's all we have there. Now the next thing that we're going to do is we're going to calculate the transformed coordinates here using our little formula. So the formula, remember, is you take your x values, you divide them by k. So I would take my x's and I would divide them by 1/2, which is the same as multiplying by 2. Then we subtract d, in this case is 60. So there's that 2x minus 60. For the y values, I multiply them by a, and a is 2. And then I add on c, and c is 1, so 2y plus 1. So I'm going to take each of these values here, and again, if you don't know this method, you don't have to do this method. You pick the method you already know. So I'm going to take 0, 1, and I'm going to transform it. I'm going to transform it by subbing it into the equation here. So I'll show you all the work here, but normally you wouldn't need to show this work. I'm going to do 2 times 0 minus 60. Whoops, that should not be a, that should be a comma right there. Minus 60, comma, and then 2 times my y value. So this is over on my left. This is my x, this is my y. Subbing in 1 for y, and then plus 1. So the coordinate is going to be -60, comma, 3. So that's the coordinate I'm going to graph. So 0, 1 from the parent function got transformed to -63. 90, 0. So x is 90, y is 0. I sub it in up here, look at the top. I sub it in up here for x, and I sub in up here for y, those two values. Sub them in, and you get 120, comma, 1. So that means 90, 0 got transformed to 121. Put in 180 and -1. Sub that in to the little equation at the top. That gives me 300. And -1 times 2 is -2 plus 1 is back to -1. 270 and 0. Subbing that in, I get 480 and 1. And 360 and 1. We're getting bigger now, 660 and 3. Now I have to graph it. So looking at all of my values here, there's my x-axis. So I'm going, my highest value is a 3 on the y, my lowest is a -1. And then looking at my x values, I'm going to put my y-axis about there. And I'm going to count by 30s. I'm going to count by 30s on my scale, but I'm only going to label the 90s just because it gets crowded. It takes a long time if you start labeling everyone. So I'm going to label by 30s, but I'm just going to count this first one as a 90. All right, I've got my scale on there, and now these are the points I'm going to graph. So I'm just going to put the dots on the grid. Once you have your dots on, your 5 significant dots, they come from the significant values on your parent graph. I should have mentioned that up here. These are the significant points, 5 parent coordinates that come from the cos graph, the max, the min, and the equation of the axis. So we see where they all transform to. Now I can see what my shape is going to look like, and I'm going to connect them with a smooth curve, not with straight lines or with zigzags. Okay, the question said 1 cycle. So I've done 1 cycle here of the sinusoidal function. I got my coordinates first so that I could figure out how to set up my scale to make sure I could fit 1 cycle on, because it was horizontally stretched because of that k value of 1/2. How can we check? There's 2 ways you can check. First of all, it should look, once you put the points on, now mine's kind of bumpy, it gets a bit bumpy in here, but it should be symmetrical, kind of sinusoidally symmetrical, meaning it's not necessarily, depending on if you're graphing sine or cos, it's not always going to be necessarily a vertical or horizontal reflection, but it should have some nice symmetry in there. This one does. You can also sub in one of your new coordinates. You can pick one of the coordinates that we got here, and you can sub it and go to the original equation, sub in the x value. So say the 120, you sub in the x value here, and when you do the brackets and then find cos of that value, multiply by 2, add 1, you should get, for your y value, a 1. So that's a way to check your calculations by subbing it right back into the original equation. The last thing we want to do is just come up with some characteristics from the function. First of all, the phase shift means based on the parent function, has it shifted left or right? And we already have this from looking at the equation. We know that we shifted 60 units to the left. The range, so it's going to be hard to fit this in here. Y is an element of real numbers such that I'm going to write below it here. My low value is a -1, less than or equal to y, less than or equal to my high value is a 3. There's my range. My period is equal to 360 divided by the k value. In this case, we've got 360 divided by 1/2. 360 divided by 1/2 is the same as 360 times 2, 720 degrees is my period. So remember, the period means, looking down on the graph here, the period means from a max to a max. That distance in between those is a period. From a max to a max. Okay, equation of the axis. The equation of the axis is just your c value. So that is, the question says equation, so I'm not just going to put a 1 there. The equation of the axis is y equals 1. And the amplitude is the a value in front, that's a 2. So those are all the features, summary of trigonometry and graphing sinusoidal functions from grade 11. Let me know if you have any questions.